we're going to start out with kind of a pseudo proof of an identity we're going to use a lot. And it's just kind of something handy that I'll do. I wouldn't even copy it down. We'll start out with 1 equals 1. Pretty simple, right? So it'd probably be better understood, though, if I said, well, let's do minus x and then plus x. And then minus x squared and plus x squared, and so on. Just keep on doing that, forever. Now that's much better understood. Great. But let's play around with this. What I'm going to do is I'm going to factor out a 1 from that first term, 1 minus x. And from this next pair, this one right here, I can factor out an x. And that leaves behind, well, 1 minus x. And from the pair behind that, this pair, I can factor out an x squared, right? If I factor out an x squared plus x squared, that leaves behind, well, 1 minus x. And I think you can kind of see the pattern here. Now, keep in mind that's still equal to 1 on the left-hand side. And what I'm going to do is I'm going to factor out that GCF. So, just a quick way to establish an identity that I want to use. It's going to be 1 minus x times 1 plus x squared plus x cubed, and so on. If I divide this, both sides, by 1 minus x, then I get 1 over 1 minus x equals 1 plus x squared plus x cubed, and so on. In other words, the sum from n equals 0 to infinity of x to the n. That's the identity that I wanted to use. We're going to use this a lot. This one's going to get a lot done for us. So, there's a few of these that I would recommend that you memorize, and this would be one of them. Have this one memorized. So what can we do with this? We got this little wonderful series. How can we use it? Well, we're going to use it to find different functions. Functions that we want. Functions that are asked for. So we'll start with problem number 8. Which asks us for a series for h of x equal to 1 over 1 minus 5x. Okay. Well, we're in pretty good shape here. They want this series centered at c equals 0. So that's good. That's going to make our life even easier here. Now, if you compare this series here to this series here, the only difference is that instead of an x here, I've got a 5x. So I'm going to take that 5x and plug it in for x. And the series that I'm going to get is going to be very similar to what I have up here. It's going to be the sum from n equals 0 to infinity of 5x to the n. Let's also determine its interval of convergence. Its interval of convergence is going to follow from the fact that this is a geometric series. So the absolute value of 5x has to be less than 1, and I'll be kind of formal for this one. I'm not going to do it for most of these. You can split this up as the product of the absolute value of 5 times the absolute value of x. In other words, the absolute value of x has to be less than 1/5. We don't really need the absolute value on this. What's the radius of convergence here? Radius of convergence is 1/5. The interval of convergence would be negative 1/5 is less than x is less than 1/5. And you can check the endpoints. You're not going to get convergence at either endpoint. So that's it. What if you had something centered someplace other than 0? Well, we'll get to that. Let's look at problem number 10. Are we okay with the first one here, problem number 8? It's a nice friendly one to start with. Okay. Problem number 10, our function is 3 over 2x minus x, so that's f of x equals 3 over 2x minus 1. Now, in this one, I want to center at, where is it, x equals 2, or c equals 2. Center equals 2. So, eventually, what I'm going to do is I'm going to rearrange this to get it to look like this, and then I'm going to use this identity. But I got a lot of work to do that. First thing I'm going to do is I'm going to change the order of terms in the denominator. I want a 1 here. So to do that, I'll factor out a negative 1 from the denominator, negative of 1 minus 2x, and then conveniently I'll kick that negative up to the numerator. So I've just reordered things a little bit. But now I need something that's centered at 2. And if it's centered at 2, that means I'm going to have a term like this, x minus 2, someplace. Because x minus 2 is going to have a center at 2. So that has to be part of my denominator term here. And I got to be pretty careful. If I replace x with x minus 2, now I'm getting something that has a center of 2, but I've changed the value of my denominator. Let's take a look at what this would be. It'd be 1 minus 2x plus 4. So really, by replacing this with x minus 2, the net effect is that I've added 4 to that term in the denominator. To balance it out, if I add 4, what else would I have to do? Subtract 4. So I'm going to put the subtract 4 here. All right. Now, let's get rid of this. These are like terms, so I can combine those. That becomes negative 3, and then negative 3 minus 2 times x minus 2. Okay, still headed in the right direction. In order for this to, or in order for us to take advantage of this, we got to make it look like this. So I got to get a 1 here, and a 1 here, and a minus something here. So what I can do is I can factor out the negative 3. So negative 3, negative 3. If I factor out the negative 3, that's going to leave behind a 1 plus 2x minus 2 over 3. If you check by distributing, you'll see that you get negative 3, and then this and this will cancel, leaving you with a negative 2 times x minus 2. So this and this are equal. I'm getting closer. Remember, my goal is to try and get this to look like 1 over 1 minus x. And I'm getting really close. Is there anything I can do here? You can cancel the negative 3's, right? So it's going to be 1 over 1 plus 2 times x minus 2 over 3. I don't really need the brackets anymore. I just left them so you can see what we had. See how they're pretty much the same. And I'm almost there. The only thing wrong is I got a plus here and I need a minus. So what I'll do is add the opposite, or I can turn this into a subtraction like this. 1 minus negative 2 times x minus 2 over 3. So this. Now, it took a lot of work to get here, but this term right here is taking the place of the x that I had in my original formula. That one I derived kind of by hook and by crook, but that formula is where I need to substitute this in for x. So that's going to be the sum from n equals 0 to infinity of negative 2 times x minus 2 over 3 to the nth power. Now you can clean this up in a lot of different ways. That's fine as it is right here. Nothing wrong with that at all. And you can split off the negative. You could have negative 1 to the nth power, 2 to the nth power, all this stuff to the nth power. But there's nothing wrong with it as is. The one last thing we have to do is determine the interval of convergence. The nice thing for us is this series. Does anyone recognize what kind of series this is? What series? You could use the root test to figure out the convergence, but we don't have to work that hard. It's a geometric series, right? You just have something to the nth power. So a geometric series is going to converge when this radius, when that r, is less than 1. So I want the absolute value of negative 2 times x minus 2 over 3 to be less than 1. So that's going to be, let's see, we can get rid of the negative because we're taking the absolute value. It's going to be negative 1 is less than 2 times x minus 2 over 3 is less than 1. You know, let's multiply both sides by the reciprocal of 2/3. That is, multiply both sides by 3/2. 3/2 times this is going to give me negative 3/2. 3/2 times this is going to cancel everything out. So just will be left with x minus 2 is less than 3/2. I could have done that up here, and that would have made obvious that my radius of convergence is 3/2. Last but not least, let's add 2 to all three parts of the inequality, and I'll get 1/2. 1/2 is less than x is less than 7/2. So that's your interval of convergence. Once again, it's not going to converge at the endpoints. Let's actually see that. It's kind of hard to imagine that this kind of stuff actually works, that somehow or another this is really equivalent to that original function that we started out with. That is, this is equal to 3 over 2 minus x, or 2x minus 1. That should be true on our interval. Let me see if I can't do that for us. Let's see. Desmos. There we go. So here's our function. Looks like that. And we want to focus on the interval from 1/2 to 3.5. So let me just shut this off and focus on this interval. Here's our series. So let me light that up. This is when you don't have any, you have one term. You have n equals 0. But let's start adding terms. N equal 1. All right, we match the derivative there. N equal 2, 3, 4. And pretty soon, what happens? It's getting pretty close, right? Now, outside that interval, if you get past 7/2, it's not converging so well. And the graph is a little bit too tall for me to see what's happening at 1/2, but, you know, it's pretty good. You're just seeing it alternate back and forth because of whether or not you have an even or odd polynomial. But on that interval of convergence from 1/2 to 3.5, boy, that's looking really good. I mean, these things are identical. I mean, I could zoom in an awful lot, and you're not going to see any daylight between these two functions. They're just equal on that interval. Outside that, well, you're on your own. But inside it, you're in good shape. That's cool. So you're replacing a function by an infinite series polynomial. Nice. Let's try another one. Problem number 16. Is there anything on problem number 10 that you'd like me to review a little bit more? Maybe a detail that I went by a little bit too fast? Doing okay on that one? Time for some more jokes? All right. All right. Problem 16. F of x is 5 over 5 plus x squared. Okay. So we're going to play the same game that we did last time. Remember, overall, what we're trying to make this function look like is this. We've got to get it to look like this. So here's an easy way to start. I want to make that 1, so I'll factor out the 5. 5 times 1 plus x squared over 5. That's pretty good. And something else happens that's pretty nice, right? What is it? Yeah, the 5s cancel, right? Those disappear. So now you're left with 1 over 1 plus x squared over 5. We're pretty close. What's the one big thing that I got to take care of? Yeah, you got to change the denominator to a minus. Now, I can't just change it to a minus. I'll do minus the opposite. So it's going to be 1 over 1 minus negative x squared over 5. That becomes my x in this formula, that whole thing. Now remember, this is the sum from n equals 0 to infinity of x to the n. So this is going to become the sum from n equals 0 to infinity of negative x squared over 5 to the n. Let's find the interval of convergence here. This is going to converge when the absolute value of this x squared over 5 is less than 1. I'm ignoring the negative because negative inside the absolute value, once you take it out, it's going to disappear. That's going to be x squared is less than 5. This is going to turn into, let's see, how do I want to explain this here? Well, there's kind of a formal way to do this, and I think I mentioned it in the last section. That I've got a whole video on this stuff. It's my Math 1150 solving polynomial and rational inequalities one. I just kind of want to jump to the happy ending, but that would be depriving you of what you should know. Let me kind of give you a quick review of this. What you need to do is you need to get 0 on one side. So it's x squared minus 5 is less than 0. When is that going to be true? If you factor this as to x minus the square root of 5 and x plus the square root of 5, actually equal to 0, that gives you 2 points where it's equal to 0. Negative root 5 and positive root 5. If you plug in values of x to test this inequality, let's choose some in each of these intervals. some to the left of negative root 5, something like 6. 6 squared minus 5 is the 31, which is positive. If I choose something in the middle, like 1, 1 minus 5 is negative. And outside that interval, choose, say, I think I chose 6 by accident. 6 would be over here. 6 and negative 6 give me the same thing. But the point is, I want to know where this is less than 0, which is going to be that middle interval. So my solution is negative root 5 is less than x is less than root 5. I'm not really comfortable with you taking the square root on both sides, although it kind of looks like it does sort of work, but yeah, it's not really that kosher. Okay. Let's see. If we test the endpoints, I don't think we're going to get the endpoints to work. So this is your interval of convergence right there. The important part to see here is the tricks we did to get it into this form right here. We factored out this so that we had a 1 here. We used the double negative, and then we were able to get the interval of convergence based on this term here. So those are the tricks that we're working with consistently. Anything on 16 before I do problem number 18? All right, problem 18. H of x is x over x squared minus 1. And again, our goal is to rewrite this using a series. We need to manipulate it into something that looks like 1 over 1 minus x. So that's kind of like your near-term goal. What kind of things do you think we can do? What would be a good first step? All right, switch the order in the denominator, right? Factor out a negative 1. It's going to be 1 minus x squared. And I'll put an x here. Let me do this. I'm going to do kind of two things here. I'm going to factor out the x from the numerator and the negative 1 like this. So it's going to be negative x times 1 over 1 minus x squared. That looks pretty good. In fact, it looks really good. Do I have to do much more? No. This is just going to be negative x times the sum from n equals 0 to infinity of x squared to the n. That's already in your nice form. All we did was take advantage of the fact that we had that factored. And we turn this part into your infinite series. We can leave the negative x out in front. Nice. The radius of convergence is when the absolute value of x squared is less than 1, which is going to be negative 1 is less than x is less than 1. let's find a series, for example, for 1 divided by 1 plus x squared. You find the series for that one. All right, looking good. So the trick in this one is pretty simple, and we used it a couple times. We'll rewrite that as 1 minus negative x squared. This term becomes your x, so that's going to be the sum from n equals 0 to infinity of negative x squared to the nth power. You can clean this up a little bit if you'd like. You don't have to leave it like that, or you can leave it like that. It's going to be the sum from n equals 0 to infinity of negative 1 to the nth power times x, to the nth power times x to the 2n, like that. So, same thing, same series. It's going to have, as its interval of convergence, the same thing that we had up here. But what I want to get to is something a little bit more fun, and that is this. What if I integrated this? What if I integrated 1 over 1 plus x squared dx? Does anyone remember what that integral gives me? The arctangent. Excellent. So tan inverse of x. But let's integrate the series over here. So if I integrate the series, that's going to be the integral of the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n, dx. Now a lot of this stuff here doesn't depend on x, so I can take it out of the integral. So that's going to be the sum from n equals 0 to infinity of negative 1 to the n, just negative 1 to the n, the integral of x to the 2n dx. Okay, good. What's that integral? Perfect. Remember, you add 1 to the exponent and divide by that same exponent. So great. So this is a series for the inverse tangent. Wow. Now, let's check its interval of convergence. So if we're going to check its interval of convergence, we want to know where this is, where it passes the ratio test. So let's see about that. So let's see. A sub n plus 1 is going to be negative 1 to the n plus 1 times x. And you got to be careful here. 2 times n plus 1 over 2 times n plus 1 again. We've kind of seen this. We've seen this exact one earlier today. Yeah, I think this we saw this exact one earlier. Anyways, negative 1 to the n plus 1 times x to the 2n plus 2 plus 1 again would be 2n plus 3. 2n plus 3, like that. Then, I don't know, somehow I feel compelled to do this. Since it's not on the missing video for section 9.8 part 1, we can do it here. The limit as n approaches infinity of of a sub n plus 1 over a sub n. It's going to be the limit as n approaches infinity of x to the 2n plus 3 over 2n plus 3, ignoring the negative 1s here, times the reciprocal of this term, 2n plus 1 over x to the 2n plus 1. The difference in these exponents here and here is 2. This minus this is going to leave me with an x squared in the numerator. So it's going to be the limit as n approaches infinity of x squared times 2n plus 1 over 2n plus 3. That x squared comes out in front, and the limit is 1. 2n plus 1 over 2n plus 3. So we get the absolute value of x squared, and we played with this before, so I'm not going to go through all the details. That means that this is going to converge on the interval negative 1 to 1. Nice. But you got to check the endpoints. And something interesting happens at the endpoints. Let's check at x equal negative 1 first. At negative 1, testing in this series here, so let me rewrite that here. Sum from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1. We would end up with the sum from n equals 0 to infinity of negative 1 to the n times negative 1 to the 2n plus 1 over 2n plus 1. Adding the exponents, I get the sum from n equals 0 to infinity of negative 1 to the 3n plus 1 over 2n plus 1. Is that going to converge? Yeah, converges. by the AST. 3n plus 1 is going to alternate. 2n plus 1 is simply going to be negative 1 forever. But 3n plus 1 works. Let's take a look at the other endpoint at x equal 1. At x equal 1, this series gets pretty simple pretty fast. N equals 0 to infinity, negative 1 to the n, 1 to the 2n plus 1 over 2n plus 1. Basically, the sum from n equals 0 to infinity of negative 1 to the n over 2n plus 1. Do I get convergence there? Parth? Yes. Converges by the AST. So my interval of convergence is negative 1 is less than x is less than... Negative 1 is less than or equal to x is less than or equal to 1. That's my interval of convergence. So I got both endpoints. But what's interesting is this series right here. Let's take a look back at what we've got. We've got the tangent inverse of x equals the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1. So that's what we established here. We've got the inverse tangent, the arctangent. And this works at negative 1 and 1. In particular, let's take a look at what happens at 1. Tangent inverse of 1 is the sum from n equals 0 to infinity of negative 1 to the n over 2n plus 1. 1 to the 2n plus 1 just disappears. It's just 1. So what does that series look like? What would the first few terms in this series be? Well, at n equals 0, you get this to the 0 power divided by 1. So 1 divided by 1 is 1. Minus, at n equals 1, now what are you going to get? Negative 1/3 plus 1/5 minus 1/7 plus 1/9, and so on. Now that's on the one hand. Does anyone remember what the arctan of 1 is? What angle has a tangent of 1? And in radians? Pi over 4. So wow. Ooh. Check out that result. That's a really cool series. Pi over 4 is just the reciprocal of the alternating series of odd numbers. So, yeah, kind of neat. I don't think I said that quite right. It's the alternating series of the reciprocals of the odd numbers. Yeah, that works. So, this is called Leibniz series. I think Leibniz formula. It's a very slow-going series. If you wanted to try and figure out the digits of pi using this series, it would take you a long time to get a good approximation to pi. But it is kind of a cool-looking series anyways. This, by the way, is really my long version of the answer to problem number 52. If you look at problem 52, they ask you to explain, what this value is. And that's exactly what we got. It's the inverse tangent of pi over 4. Okay. Two more in this section. Problem 32 and problem 34. problem 32 is the integral from 0 to 3/4 of the arctan of x squared. Now, I've shown you a lot of tricks for integration. We did integration by parts. We did integration by partial fractions, substitutions. None of them is going to help us out here. None of them. You're stuck. But we do have a little bit of something we can work with, and that is the arctangent of x. Oops, I did, sorry. The arctangent of x has a series that we know, and that series is the sum from n equals 0 to infinity of -1 to the n times x to the 2n plus 1 over 2n plus 1. Okay, that's nice, but I don't have just the arctangent. I got the arctangent of x squared. All right, that's not a big deal. The arctangent of x squared, arctan of x squared, is going to be the sum from n equals 0 to infinity of -1 to the n over 2n plus 1 times x squared to the 2n plus 1. So all we're doing is we're substituting in x squared there. And let me simplify that a little bit here. This is going to be the sum from n equals 0 to infinity of -1 to the n. 2 times this is going to be x to the 4n plus 2 over 2n plus 1. These two things on the interval -1 to 1 are interchangeable. I can use one just as good as I can use the other. And here's the amazing part. I can replace this by this. The sum from n equals 0 to infinity of -1 to the n, x to the 4n plus 2 over 2n plus 1 dx. Oops. Here. Now, the stuff that doesn't involve the x, I can pull outside. Pull it out in front of the integral. So, what happens there? That's going to become the sum from n equals 0 to infinity of -1 to the n, 1 over 2n plus 1 times the integral from 0 to 3/4 of x to the 4n plus 2 dx. This is something we can integrate. -1 to the n, 1 over 2n plus 1, 0 to 3/4. What's the antiderivative of this term? Con? Thank you. X to the 4n plus 3 divided by 4n plus 3. Now, the 4n plus 3 is a constant term, so I'm going to kick that out in front. N equals 0 to infinity, -1 to the n, 1 over 2n plus 1 times 1 over 4n plus 3 times this evaluated at 3/4. 3/4 to the 4n plus 3 minus 0 to the 4n plus 3, which of course is just 0. So we get something like this. Whew. Almost there. Sum from n equals 0 to infinity of -1. Let me put this all together. I'll write 3 to the 4n plus 3 in the numerator. 2n plus 1 times 4n plus 3 times 4 to the 4n plus 3 in the denominator. And I need an n here. So that's my integral. Yay. But how many terms do I need in order to, get a reasonable approximation? In the problem, they asked us to approximate it to the nearest 1,000th. Now, remember on the test, we had a problem just like this. How far do you have to go out? You have to go out until you find a term that's less than 1/1000th. And that's the first term that you can leave off. So, my suggestion is to do that on our calculator. We'll see if we can't be a little bit clever about how we do this. I don't want to get too clever because I think you guys are getting tired, so let's just do a kind of a brute force approach. In the numerator, I've got 3 to the 4n plus 3. So 3 raised to the, oops, how about 3? 3 raised to the, we'll do 4x plus 3. Divided by, and then I need a whole bunch of parentheses here. Parentheses and then parentheses again. 2x plus 1 times 4x plus 3 times, and I don't really need to hit the times, it's just going to be 4 raised to the 4x plus 3. Exit the exponent with the little right arrow key, and then I need another parenthesis around the entire denominator. So I think I'm in good shape there. Let's go to the table. Make sure your table is set up so that you can plug in the values of x that you want. So that means independent is set to ask. Second table, and there we go. So if you plug in the first few values, if you want to see all the digits, put the cursor on the y value. I'm looking for something that's less than 1/1000th. So there you go. 2 terms. I need 2 terms to get this in this series. So those 2 terms will give me an approximation that's accurate to less than 1/1000th. If you actually plug in the numbers, they're not exactly really pretty or friendly. The first 2 terms are 1/64th. Sorry, I keep on going the wrong way. 1/64th minus 1 over 1152. So that's your approximation to the integral. Just need those 2 terms. Let's kind of check that. That's an amazing result. That after a fair amount of work, that you just need those 2 fractions to approximate that entire integral. What's that? No, 64. 64. Thank you. So let's compare. Let's see. 1 divided by 64 minus 1 divided by 1152. And I want a decimal value there. Let's see. Mode. Answers and decimals. There we go. 0.014, etc. Let's compare that to the actual integral numerically. You hit the math button. 9th one down is your integral. The integral from 0 to 0.75, which is 3/4 of the inverse tangent, arctan of x squared dx. Let's see how we do. Oops. I'm off here by something. Rats. Should be a lot closer there. Where did I make a mistake? Oh boy. 2n. You know what? Something's wrong. What's wrong? That one should work out pretty good. Okay. You know, I'm a mistake. I don't think these are right. Let's see. If we put in a 1, then I would get, you know, I don't want to hold you up. Let me put you on break. I'll finish this out. I'll figure this out while you're on break. But I think these two things are wrong here. These numbers come from integrating this to 0 to 1/2. So I've made a mistake there. Let's see. So to fix this, I'll do, the numerator is going to be 3 raised to the 4x plus 3. And the denominator is going to be the product of 2x plus 1 times 4x plus 3 times 4 raised to the 4x plus 3. Now when I go to my table, I'll get the numerators and denominators. So let's also do one last thing here. Let's find the ratio of these two. You can hit the vars key, y vars, want y1 divided by, and then go back and do vars y2. So I get the ratio of these, and that ratio is going to be less than 1/1000th. Again, at the after the third term. So really, those first two should be good enough. So let's see. That first one is going to be 27 over 192 minus 2,187 divided by, oops, 344,064. So let's try that one and see if that one works. So here, and then 27 divided by 192 minus 2187 divided by 344,064. Whoo! Thank goodness. If that didn't work, I would have been so bummed, man. All right, so yeah, I just had the wrong fractions there. Cool.